In December 2021, the telescope folded up like origami launched off the coast of French Guiana aboard an Ariane 5 rocket, then spent the next month slowly unfolding itself in the vacuum of space, a full million miles from Earth, in a sequence of deployments so intricate that engineers openly described it as the riskiest part of the entire mission. 7 months later, in July 2022, after a lengthy commissioning period spent calibrating every single instrument on board, it finally opened its eyes for the first time and began real scientific observations. And within its very first year of operation, the James Webb Space Telescope did something almost no one on the mission team fully expected, even after years of planning. It didn't just take beautiful pictures. It found galaxies that, according to our best model of how the universe works, shouldn't exist at all. Not unusual, not surprising. A genuine, published, peer-reviewed problem serious enough that astronomers gave it its own name, the impossible galaxies problem. And depending on which paper you read, that problem is either already solved, or it's still very much alive in 2026, quietly chipping away at one of the most successful scientific models ever built. By the end of this video, you'll understand both sides of that argument, using the actual published research, not the hype. And I'd genuinely rather you walk away from this with an honest, slightly messy picture of where the science actually stands right now than a tidy, satisfying fake answer that quietly falls apart the moment you go read the papers yourself. Let's start with the model Webb was supposedly breaking, because you can't understand why any of this mattered without it. For decades, cosmologists have relied on something called the Lambda-Cold Dark Matter model, usually just written as Lambda-CDM. It's not some fringe theory. It's the closest thing modern astrophysics has to a working operating system for the universe, built up over decades of observations of the cosmic microwave background, galaxy surveys, and the expansion rate of space itself. Lambda-CDM makes a very specific prediction about galaxies in the early universe. Right after the Big Bang, everything should have started small. Tiny clumps of gas slowly pulling together under gravity, slowly collapsing into the first protogalaxies, slowly assembling into the kind of large, structured galaxies we see around us today. Slowly is the key word. According to the model, building a genuinely massive, mature-looking galaxy should take billions of years. It's worth being specific about what successful actually means for a model like this, because it's easy to hear just a model and assume it's shakier than it actually is. Lambda-CDM correctly predicts the large-scale pattern of how galaxies cluster together across the universe. It correctly predicts the precise ratios of light elements, hydrogen, helium, and lithium, that were forged in the first few minutes after the Big Bang. It correctly predicts the fine details of the cosmic microwave background, the faint afterglow of the Big Bang itself, measured with extraordinary precision by satellites like Planck. This is a model that has been tested against an enormous range of independent evidence, spanning completely different types of measurements, and it has kept passing those tests for decades. That track record is exactly why Webb broke it, is such a serious claim to make. And exactly why serious researchers didn't just shrug and throw the model out the moment something unexpected showed up. Webb's job, in part, was to look back far enough in time to actually test that prediction directly, because looking farther away in space also means looking farther back in time, since light takes time to travel. Point Webb's infrared instruments at a distant enough galaxy, and you're not just seeing a faraway object. You're seeing light that left that galaxy when the universe itself was a small fraction of its current age. And that's exactly what happened. Within Webb's first year of science operations, multiple independent research teams, publishing in 2022 and 2023, including work led by researchers such as Rohan Naidu, Ivo Labe, Emma Curtis-Lake, and Brant Robertson, started reporting galaxies at redshifts around 10 to 14. In plain terms, they were looking at galaxies as they existed somewhere between roughly 300 and 500 million years after the Big Bang, a universe barely out of its infancy, on a cosmic timescale where the current age of everything is about 13.7 billion years. It's worth pausing briefly on why Webb, specifically, was even capable of making this kind of discovery, because the previous generation of space telescopes genuinely couldn't have done this job. Webb carries a primary mirror 6.5 meters across, assembled from 18 individual gold-coated segments that had to unfold and align themselves in space with precision measured in nanometers, after launching folded up small enough to fit inside a rocket fairing. Instead of orbiting close to Earth the way Hubble does, Webb sits nearly 1 million miles away, at a gravitationally stable location called the second Lagrange point, where it stays permanently tucked behind a tennis court-sized sunshield that keeps its instruments cold enough to detect almost unimaginably faint infrared light. That combination, a huge mirror, extreme cold, and instruments tuned specifically to infrared wavelengths, is what let it see light from galaxies so old and so distant that the expansion of the universe itself has stretched their original light all the way down into the infrared part of the spectrum. Hubble, built primarily to observe visible and ultraviolet light, was essentially blind to most of what Webb was specifically engineered to find. Without that specific infrared design choice, none of what's about to come up in this video would have been observable at all. Here's where it stopped being just, wow, that's early, and started being a real problem. According to a widely cited 2023 analysis, several of these newly discovered galaxies were not only far too early, they were far too big and far too bright for their age. Researcher Michael Boylan Colchin specifically flagged that the observed abundance of massive luminous galaxies at these early times sat in real tension with the predictions of Lambda-CDM. Around the same time, a separate team led by Avishai Deckel described the situation even more directly, stating plainly that their results reinforced photometric evidence for far more bright galaxies at these early redshifts than the standard theoretical models predicted. And the size problem wasn't the only issue. Multiple teams, including work from researchers like Charlotte Adams, Hakeem Atek, and several others publishing independently around the same period, found that many of these galaxies had physical diameters, roughly an order of magnitude smaller than Lambda-CDM would predict for objects that massive. In other words, shockingly compact, not sprawling, diffuse protogalaxies barely holding themselves together, tight, dense, already organized structures, at a point in cosmic history when they were supposed to still be a loose scatter of gas and infant stars. As Webb's survey data grew, astronomers started noticing that a specific subset of these compact, distant objects shared a distinctive visual signature: small, extremely red, and unusually bright for their apparent size when viewed in Webb's imaging. Researchers began informally calling this class of objects little red dots, and they quickly became one of the single most argued over discoveries to come out of the entire mission. Part of what made them so contentious is that they didn't fit cleanly into either of the two categories astronomers already understood. They weren't behaving like ordinary star-forming galaxies, and they weren't behaving like ordinary quasars either. Some early analyses proposed they were simply dust-reddened, extremely compact galaxies undergoing intense bursts of star formation. Other researchers, including work led by Dale Kachevsky, argued a meaningful fraction of them were actually powered by actively feeding supermassive black holes, effectively small, faint, deeply reddened cousins of the same quasar phenomenon behind the 10 billion solar mass black hole discovery. That disagreement over what little red dots actually are turned out to be far more than an academic curiosity. It would later become the single detail that helped crack open the entire impossible galaxies debate. One individual galaxy became a kind of poster child for the whole debate: GNZ11. According to spectroscopic analysis, led by researcher Roberto Maiolino using Webb's NIR spec instrument, GNZ11 is seen as it existed just 430 million years after the Big Bang, and the data described it as an object with genuinely extreme properties for its age, a level of maturity and brightness that, under the old assumptions, simply shouldn't have had time to develop yet. Follow-up analysis of that same object went on to detect a specific chemical signature: polycyclic aromatic hydrocarbons, complex carbon-based molecules more commonly associated with much older chemically enriched galaxies, sitting inside a galaxy that, by the standard timeline, should barely have had time to produce its first few generations of stars, let alone build up complex carbon chemistry through repeated cycles of stellar life and death. Then, in 2023, a separate but related shock arrived from studying quasars, the extraordinarily bright cores of galaxies powered by feeding supermassive black holes. A study, led by researcher Anna Christina Eilers, examined a quasar from less than 1 billion years after the Big Bang and found it was powered by a black hole containing roughly 10 billion times the mass of our Sun. According to Eilers and her co-authors, a black hole that size, that early, is genuinely difficult to explain using our current understanding of how black holes form and grow. Building a black hole that massive, that quickly would require it to be almost constantly gorging on infalling matter at rates close to the theoretical maximum for hundreds of millions of years, essentially without pause. A scenario that, before Webb, most researchers considered unlikely to sustain for that long. To understand why that's such a difficult problem, it helps to know how black holes are generally thought to grow in the first place. There's a natural speed limit on how fast a black hole can feed, called the Eddington limit, essentially the point where the radiation pressure from infalling matter starts pushing back against more matter, trying to fall in, throttling the feeding rate. Under normal assumptions, a black hole growing right at that limit, starting from a relatively modest initial seed mass left over from a collapsed early star, simply doesn't have enough time to reach 10 billion solar masses within the first billion years of cosmic history. The math doesn't close, even under fairly generous assumptions. That gap is exactly why researchers like Junhyung Jeon, working alongside Volker Braun and Steven Finkelstein, have spent the past few years exploring alternative pathways specifically built to explain how JWST's early supermassive black holes could have formed at all. including scenarios involving unusually massive initial seed black holes, or sustained feeding episodes running well above the traditional Eddington limit for extended stretches. None of these alternative pathways were seriously required by the data before Webb came online. After Webb, they became a genuinely active area of research, precisely because the observed black holes didn't leave researchers any other simple option on the table. Put all of that together, and you can see why astronomers weren't just mildly curious. You had galaxies too early, too big, too compact, and too structurally mature, alongside black holes too massive and too fast-growing, all clustered in the same narrow window of cosmic history that the Standard Model said should still look practically empty. Science journalist Alexandra Witz, writing in the journal Nature in 2023, summarized the mood among astronomers plainly. The findings were dazzling researchers, because stars and galaxies appeared to have been forming and evolving far earlier than anyone had expected going in. So, was the model actually broken? This is where the story gets genuinely more interesting than a simple yes or no, and where a lot of less careful coverage online just stops, right at the most dramatic-sounding headline, without following the science any further. In 2025, a team led by Katherine Chorowski, a graduate researcher at the University of Texas at Austin, working with Stephen Finkelstein, one of the lead scientists behind Webb's Cosmic Evolution Early Release Science Survey, known as SEERS, published a study that directly tackled the impossibly massive galaxy problem. Their explanation: several of the most extreme-looking galaxies weren't actually as massive as they first appeared. Instead, many of them contained rapidly feeding black holes at their centers, the same little red dots phenomenon we just walked through, and the intense friction and heat generated as gas spirals into those black holes was pumping out extra light that got misread by earlier analyses as coming from a much larger population of stars than actually existed. Essentially, an optical illusion baked directly into the measurement itself. The black hole's glow was masquerading as galaxy-wide starlight, inflating the apparent stellar mass estimates for the whole system. To pull this apart, Chorowski's team went back through the original SEERS survey data and specifically flagged which of the earlier impossibly massive galaxy candidates showed the telltale spectral signatures of an actively feeding black hole rather than ordinary starlight. Once those black hole-dominated systems were separated out and their contribution to the total light was properly subtracted, the remaining, purely stellar mass estimates for those specific galaxies dropped substantially, enough, in several individual cases, to move them from impossible under Lambda-CDM back into the range the model could actually accommodate. That's a meaningfully different finding than simply asserting the crisis wasn't real. It's a specific, checkable mechanism tested against the same underlying data that originally caused the alarm. Finkelstein himself was blunt about what this meant for the broader model. In comments describing the study's conclusions, he stated there is no crisis for the Standard Model of cosmology, arguing that a theory with as much successful evidence behind it as Lambda-CDM shouldn't be discarded without truly overwhelming proof, and that this wasn't it. But, and this is the part that matters if you actually want the honest version of this story instead of a tidy, satisfying ending, Finkelstein and his team didn't claim the mystery was completely gone. Even after accounting for the black hole glow effect, their own analysis still found roughly twice as many early galaxies as Lambda-CDM predicts. Their proposed explanation for that remaining gap is that stars in the early universe may have simply formed faster and more efficiently than current models assume, gas clouds collapsing into stars more readily than the same process does in the modern universe. That's a real, testable hypothesis. It's also, notably, still an adjustment to the standard picture, not a complete return to business as usual. And plenty of researchers think even that adjustment doesn't fully close the case. On the more skeptical side, physicist Fulvio Melia has published multiple papers arguing that the timeline problem runs deeper than just individual galaxy masses. Drawing on a broader 2024 analysis led by researcher Julian Munoz, Melia has argued that even with every reasonable modification available, the standard Lambda-CDM timeline still can't fully account for the combined picture from Webb's early galaxy data and the Planck satellite's measurements of the cosmic microwave background, specifically around what's called the reionization era, the period when light from the first stars and galaxies stripped electrons from primordial hydrogen gas throughout the universe. According to this line of argument, matching both datasets at once requires a genuinely uncomfortable amount of stretching, even after the black hole glow explanation is factored in. The specific mechanism behind this version of the argument is what's sometimes called the photon budget crisis. Reionizing the entire universe's worth of hydrogen gas requires an enormous, sustained output of ultraviolet light, pouring out from the very first generations of stars and galaxies over an extended period. If Webb's data implies that galaxies were unusually bright and unusually numerous in this early era, even after subtracting out the black hole glow effect, Then, according to Melia's analysis, the universe should have finished reionizing meaningfully earlier than what the Planck satellite's independent measurements of the cosmic microwave background actually show. You can't simply have it both ways in the same model. A universe bright enough, this early, to explain Webb's galaxy counts, while also reionizing on the slower schedule that Planck's data implies. Reconciling those two independent lines of evidence, according to this camp of researchers, may ultimately require more than just refining assumptions about star formation efficiency. It may point toward an actual missing piece in the standard cosmological model itself, rather than just an accounting error in how individual galaxy masses were measured. To be clear about where this leaves the debate, this is not a fringe, discredited argument being kept alive by a handful of outliers. It's a genuine, ongoing disagreement between researchers working with the same publicly available datasets, publishing in peer-reviewed venues, reaching different conclusions about how much of the original tension has actually been resolved. That kind of disagreement, sitting unresolved for years after the original discovery, is exactly what makes this such an unusually durable science story, rather than one that gets neatly wrapped up within a single news cycle. Then, completely independent of that theoretical argument, Webb kept finding individual objects that are hard to wave away with any single explanation. In early 2025, researchers including Thamaya Nanayakara at Swinburne University of Technology identified a galaxy nicknamed the Big Wheel, a massive galaxy with a clear spiral structure existing within the first 2 billion years of the universe. Under the Standard Model, galaxies that early are expected to be violently disturbed by frequent collisions with their neighbors, which should tear apart anything as delicate as a spiral disk long before it could fully form. Nanayakara has pointed out directly that what makes the Big Wheel interesting is precisely that combination. Genuinely massive, and yet organized into the same kind of elegant spiral shape you'd expect from a galaxy like our own Milky Way, which took billions more years to reach that same structure. What makes the Big Wheel particularly awkward for the Standard Model isn't just its age, it's the specific type of structure involved. A large, disorganized blob of stars at an early cosmic age is relatively easy to explain away. Gravity clumping matter together doesn't require much fine-tuning to produce something messy and irregular. A thin, delicate spiral disk is a completely different challenge, because that kind of structure requires a long period of relative calm, enough time for stars and gas to settle into a flat, rotating disk without getting disrupted by a major collision or violent merger along the way. Finding that level of structural order within the first 2 billion years genuinely surprised researchers who study early galaxy formation, precisely because the standard simulations built to predict early universe conditions generally assume that kind of calm, settled environment simply wasn't available yet. And in 2025, a separate team, led by researcher Rohan Naidu, confirmed, through direct spectroscopy, a galaxy at a redshift of 14. 44, nicknamed only half-jokingly in their own paper, a cosmic miracle, describing it as remarkably luminous for an object at that almost unbelievably early point in cosmic history. A redshift of 14. 44 corresponds to a universe that was only a few 100 million years old, placing this among the very earliest individual objects ever confirmed through direct spectroscopic measurement, rather than estimated indirectly from imaging alone, meaning researchers aren't just inferring its distance and brightness from color and shape, but confirming it directly from the specific wavelengths of light detected, the same rigorous method used to confirm GNZ11 years earlier. So where does that leave us, honestly, in the summer of 2026? Not at a clean final answer in either direction, and I think that's actually the most interesting place for this story to sit, rather than a manufactured one. The most extreme version of the impossible galaxies crisis, the idea that Webb's discoveries flatly disprove the standard model of the universe, does not appear to be where mainstream cosmology has landed. Careful follow-up work, especially the black hole glow explanation from Chwarovsky and Finkelstein's team, has resolved a meaningful chunk of the original tension. But a meaningful chunk resolved is not the same sentence as problem solved. There's still roughly double the number of early galaxies that the standard model predicts, still individual objects like the Big Wheel that don't have a fully satisfying explanation yet, and still a genuine ongoing argument among specialists in the reionization era about whether the timeline can be stretched far enough without breaking something else in the process. This is also, honestly, exactly what real scientific progress is supposed to look like, even when it doesn't make for as clean a headline as a single video title can promise. Lambda-CDM has survived incredibly strong, incredibly specific challenges before, and every time, the response from the scientific community wasn't to simply throw the model away the moment something surprising showed up. It was to dig into the data, propose specific physical mechanisms that could explain the surprise, test those mechanisms rigorously against new observations, and only then decide whether the core model needed to change or just needed refinement around the edges. That's precisely what's happening right now in real time. with early universe cosmology, and Webb is the instrument making that entire argument possible in the first place, by handing scientists more raw, specific checkable data than they've ever had access to for this era of cosmic history. Why should any of this matter to you if you're not a professional cosmologist? Because the question underneath all of this isn't really about one telescope or one graduate student's thesis. It's about whether the basic story we tell about how everything, galaxies, stars, eventually planets, eventually us, came to exist is actually correct in its broad strokes, or whether there's a genuinely undiscovered piece of physics still hiding in the very early universe that we haven't identified yet. Webb hasn't definitively answered that question either way. What it's done is force the people whose entire careers are built on getting that answer right to go back, recheck their assumptions, and do the harder, slower, less flashy work of actually testing them against real data, which is precisely what a functioning scientific process is supposed to do when reality throws it a curveball. It's also worth being upfront about a few of the more speculative ideas that have popped up around the edges of this debate, mostly in preprint papers rather than mainstream peer-reviewed journals, because you'll likely run into them if you search around this topic yourself. Some researchers have proposed alternative cosmological frameworks entirely, modified theories of gravity, alternative expansion histories, or scenarios involving early populations of primordial black holes, specifically designed to make the timeline problem disappear without needing either the black hole glow explanation or faster early star formation. None of these alternative frameworks currently have anywhere near the broad observational support that Lambda-CDM has built up over decades, and most working cosmologists still treat them as speculative rather than serious competitors to the standard model. I'm mentioning them here not because they're likely to be right, but because being upfront about the fringe of a debate is part of representing it honestly, rather than only showing you the two most mainstream positions and pretending nothing else exists. Zoom out far enough, and this entire episode is actually a pretty good demonstration of how science is supposed to work when it's operating correctly, even though it rarely gets covered that way. A surprising result showed up. Multiple independent teams rushed to check whether it was real. Specific, testable mechanisms were proposed to explain it. Some of those mechanisms held up under scrutiny and reduced the size of the original problem. Others are still being actively contested using the exact same public datasets. Nobody with real standing in the field is quietly sweeping the remaining discrepancy under the rug. It's sitting right there, openly argued about, in papers being published this year. That's not a system failing. That's a system doing exactly what it's designed to do, just slower and messier than a punchy video title can really capture. If you want to actually verify any of this instead of taking my word for it, every specific claim in this video is drawn from named, published, peer-reviewed research, including work by Boylan-Kolchin, Dekel, Maialino, Eilers, Chorowski, Finkelstein, Melia, Munoz, Nanayakara, and Naidu, spanning 2022 through 2025, plus reporting from Nature and Universe Today covering those results directly. I'll leave the specific papers and articles referenced below, so you can go check the sourcing yourself, which is exactly what I'd want you to do with a story making claims this significant. That's also, honestly, the single biggest difference between a video like this one and a lot of the lower effort space content circulating online right now. Anyone can string together dramatic language about telescopes and mysteries, but not every video actually hands you the names, dates, and papers to go check for yourself afterward. So, did James Webb actually break science, or did it just do its job better than anyone expected, forcing our best model of the universe to earn its keep all over again? Based on where the actual research stands right now, the honest answer is somewhere in between, and that gap hasn't fully closed. Some of the most dramatic sounding claims from 2022 and 2023 have genuinely been walked back with better data. Others are still sitting there, unresolved, in papers being published as recently as this year. If you want to know which way this settles, because it will eventually settle one way or the other as more data comes in, subscribe, because we'll be covering the next major update on this exact debate the moment it's published, with the same sourcing and the same honesty, no invented drama required. Because the real story here has never needed any exaggeration to be worth your attention. Let me know in the comments which side of this you land on. Resolved illusion or genuine crack in our best model of everything.